So I don't know as our textbook really kind of emphasizes Einstein's special theory of relativity, but I wanted to just kind of lay it out a little bit and tell you the overall outcomes of Einstein's special theory of relativity. I'm no expert in the area, as you will see, but I think it's important because black holes and neutron stars, and the crazier an object, the more dense an object, at great masses and high speeds, objects tend to fall into this area of this type of physics, Einstein's physics. And so in order to understand Einstein's or special theory of relativity, you need to know that we're going to be talking about these frames of reference, and for instance, a frame of reference that's going very fast, or a frame of reference that's near a very dense object. That that regardless of your frame of reference, the speed of light, the velocity of the photons either coming to you or leaving your area must be going the speed of light. Okay. Secondly, that if you have some sort of measuring device that measures mass or measures length or measures time, that your measuring device will be behaving the same. Rulers all will act the same within your frame of reference or outside your frame of reference. You know, scales will act the same, okay? So then the other thing is, or kind of I think at the crux of the special theory of relativity, is the fact that that speed of the speed of photons moving is not additive. For instance, we're so used to adding speeds. If you have a train moving towards you, you're in a car and the train's moving towards you at 30 miles per hour, and you're moving towards the train at 60 miles per hour, then you kind of add those speeds and you think, well, you guys are cutting the distance between you and the train at what, 90 miles per hour. But we can't do that with photons, or we can't do that with objects with radiation traveling at the speed of light. So for instance, we have a very fast car here traveling at half of the speed of light, which is very fast. And the photons leaving that lamp are traveling at 1 times the speed of light. We can't say that from the frame of reference of the car that those photons are traveling at 1.5 speed of light. That doesn't work, because that's incorrect. That would violate what I told you a little bit ago, the fact that objects cannot go faster than the speed of light. So there's this concept known as simultaneity, and just check out my playlist, okay? So there are certain consequences of this. So I kind of, like I said, wanted to kind of boggle your mind a little bit, because it boggles my mind, the fact that there are these kind of 3 fundamental results or outcomes of Einstein's special theory of relativity. And one is that the length of an object, if your object is in motion, the length of let's put it this way, the length of an object that's in motion will be shorter relative to the person who is not in motion. The stationary observer, so to speak, will think that the object that's in motion is shorter. And you're like, well, yeah, they'll think it's shorter because it's going by fast and they don't see the whole thing. It's like an optical illusion. No, it's literally shorter. Okay, now, granted, in this case, this train would need to be going very fast. Einstein's theory of relativity is these outcomes are most emphasized at objects that are traveling, approaching the speed of light. Okay, so let me go back. Did you catch that? That if you're in the train and you're measuring the distance of the train, your yardstick would read the same. Whereas if you're in a different frame of reference, if you are in the stationary watching the train move, and if you were to be able to hold a yardstick up to it, you actually would see that the faster the train goes, the shorter it becomes. Pretty cool, pretty cool. Well, this is a neat one. And this again has to do with objects that are moving quickly. If you were to have a clock, now a clock, you have two clocks. One clock is going to stay stationary here with you, and the other clock is going to, actually this has been done before, go in a jet airplane with somebody else, okay? You synchronize your clocks. And as you're in the jet airplane, your clock looks normal. It ticks off time just like normal. And of course, if you're stationary, your clock ticks off time as normal too. When that plane stops, what you will have noticed is that that clock will have ticked off less time. Time literally unfolds more slowly in frames of reference that are moving faster. And the more you approach the speed of light, the slower time will unfold. It will seem like it's unfolding normally in your frame of reference if you're the person moving real quickly, but compared to somebody's clock who is in stationary, not moving, it's moving slowly. Isn't that cool? The last one I want to talk about is the fact that, again, if you are moving quickly, okay, actually if you were to have scales in your frame of reference that were operating normally, you would see that your mass is just normal. But if you were somehow to be able to, the person who is stationary, to be able to analyze your mass is increasing. And the faster you go, your mass is increasing faster and faster. So that at some point, as you approach the speed of light, your mass is approaching infinity. So I just think that is so cool. So those were the outcomes of Einstein's special theories of relativity. I mentioned his general theory of relativity had to do with the kind of the fabric of space-time. And actually there are certain outcomes of his general theory of relativity too. Just want to touch on the fact that that gravity actually can affect time also. Okay, and like this slide says, that the more massive an object actually will make time unfold more slowly. Okay, so here we have two clocks that are placed on different celestial objects. One clock placed on the Earth and one clock placed on the Moon. Now, of course, the Moon has less mass than the Earth. So actually the Earth's mass affects how time unfolds. So time on the Earth will unfold more slowly than time on the Moon. And so actually this again is an experiment, just like the experiment a minute ago when I said you can put the same clocks in an airplane moving very quickly, or a jet, okay? So also you can do this sort of thing. And notice that not much, but that the Earth's clock has ticked off less time. Time is moving more slowly on the Earth than it is on the Moon. Okay. Well, Einstein's general theory of relativity describes gravity then kind of as dense in the fabric of space-time. And so actually we can use a technique called gravitational lensing to make use of the fact that objects as massive as perhaps even the sun will bend light from distant objects as it makes a dent in the fabric of space-time. So this first little image I'm showing you actually is to show you that, for instance, a star can be, the star that's behind the sun from our perspective, actually this rays can be bent and deflected so that we can see that object because of the distant star's light rays are being bent as it approaches the sun. And we can use this technique as the gravitational, in a technique called gravitational lensing to magnify images, distant images, by using how objects between us and that image dent the fabric of space-time. The other one, actually, we didn't talk much about it, but Mercury does kind of have this over time kind of crazy sort of trajectory around the sun, and that has to do with it actually is responding to how the sun is making kind of a dent in the fabric of space-time. So another thing, or something related to denting the fabric of space-time, is this, that light that is escaping the influence of dense objects, such as a white dwarf or a neutron star, kind of have to work harder to escape that kind of gravitational well. They have to climb out. So, for instance, I'm going to show you from the bottom, I have 3 images here, and we have a gal that's looking at a light. Okay, and I'm going to place this light closer and closer to this dense object. And the closer the light is placed to the dense object, notice that the color is changing. And the color is changing because it's losing some of its energy. The photons are losing energy as they can escape the gravity of that object. Okay, white dwarf or neutron star, but it loses some energy and it makes it to a longer wavelength. That's called gravitational redshift, and we see this in white dwarfs, this phenomenon. So this is kind of a nice little animation I'm going to show you on the next slide. This actually, we see I'm going to show you 2 rockets that are orbiting. You see the word event horizon, so that must be the region around a black hole beyond which no light can escape. So we see these 2 spaceships. Now notice this spaceship that is closer to the event horizon. It's kind of got, the time is red. It says 15 seconds. And so it's showing you the gravitational redshift. The other thing is, notice that the 15 seconds is slower. Only 15 seconds of time has clicked off instead of 50 seconds of time. Let me show you the animation. Again, if you have Mastering Astronomy, you have access to this. It's just a little movie, and I don't know if, I hope you can see it. So at this point we have the 2 spaceships that are equidistant from the event horizon, and if I were to stop it, I don't know if you can see that the time clicking off is the same. And for whatever reason, the one spaceship stops orbiting, and so it is destined then to fall towards the event horizon. And I don't know if, can you see it turning red? And actually here in a minute when it stops, you're going to see that the time clicked off. I'll go ahead and pause it. So we see the gravitational redshift of the spaceship. You know, we can see it, but the light has to travel out of that gravitational well, and so it loses some of its energy, so it's shifted to the red. And also notice that the time on the vessel that's near the black hole is only 1 minute and 37 seconds, and this spaceship out here, the time lapsed is 2 minutes and 35. So time is slowed for that object in the vicinity of the black hole. I just think that's so cool. So then, of course, which spaceship would you like to be in? Well, I think I'll take my chances orbiting the black hole. Neil deGrasse Tyson does a great job of talking about a way to die called spaghettification, and that's kind of what's being shown here. That basically, if you were to fall towards a black hole, the gravity would stretch you out, kind of like a, I think he uses the word like a, at first it would feel pretty good, like a nice cosmic yoga. But that's kind of, material would be kind of extruded as it fell towards the black hole.